All right, ladies and gentlemen, recording has started. So, yesterday, we started talking about reaction energy, and that was going to lead us into reaction rates. So we spent a good amount of time talking about these energy diagrams and looking at the energy of the reactants versus the energy of the products, and then classifying that reaction as endothermic or exothermic, depending on whether the energy goes up or energy goes down. And then, with these four pictures here, right, we can make a prediction from looking at the energy of the products and the energy of the reactants. Where do they start? How different are they? And then that other factor that we call the activation energy, right? And make a prediction about which reaction is most likely to occur, what's going to be easy for us to make it happen, what's going to be not so easy for us to make it happen, all those things. Okay? There are some things that we can do to increase the rate that a reaction occurs. So that's where we're going to pick it up with today. First, when we talk about something being a rate, that implies that there is a certain factor that we have to consider when examining this situation. When we talk about something being a rate, Eris, go ahead. Time. There's always a time factor that's included. So in this case here, when we're looking at the rate of a reaction, we're looking at how quickly does this reaction occur? How quickly do reactants become products? There are some things that we can do to affect the rate of that reaction, either to speed up how quickly reactants are becoming products or to slow it down. Sometimes we want to slow it down. Sometimes it happens too fast. So first, we'll start off with some physical things. Physical things without actually adding anything to the reaction or changing something in the reaction that will cause the rate of that reaction to change. First, temperature. All right? Hopefully you know, we'll talk about this more as we go along, right? What does the temperature tell us about a substance? If we measure its temperature, what is that really telling us about the substance? Mark? How fast the particles move, right? So Mark, with that being the case, increasing the temperature is probably going to do what to the rate of the reaction? Probably going to increase it, right? If the particles move more, they're going to run into each other more, reactants are going to come in contact with other reactants, and it's going to speed up that reaction. So generally, reactions go faster at high temperatures. Generally. Keep in mind, these are generalizations. Okay? All right. Good there. Okay. Another physical factor that we can take into account, surface area. A large surface area for the reactants will speed up the reaction. What can we do to something to increase the surface area? Pretty good.
Break it up.
Break it up into small pieces, right? It's the difference between a sugar cube and sugar that's all ground up, right? Generally, that sugar that's ground up dissolves into things faster, blah, 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 right? Making the pieces smaller generally increases the rate of the reaction. Okay? Again, another physical thing. We're not changing anything about the reaction, but just physically changing stuff to affect the rate. Next, concentration. If we talk about the concentration of the reactants, we're talking about how much of those reactants are actually there or how pure those reactants are, right? Generally, concentrated solutions will react faster. If we talk about something being more concentrated, right, that means there's more per unit volume or area or whatever we want to talk about, right? This would be like, I don't know if anybody actually does this anymore. Do you guys like buy frozen juice at the grocery store? You know what I'm talking about? It comes in like a can, it's about yay big, and you add like 3 cans of water to it. I don't know if anybody actually buys that anymore or not, but you know, like if you taste that, right? Yeah, it kind of tastes like orange juice, but like orange juice to the max, right? You know, or if you buy like the lemonade, it's like super, super sour, because, right, that concentration is much higher. The stuff that tastes like lemons, there's more of it per teaspoon or whatever we're looking at, right? That's going to cause that reaction or the change or the perception of it to increase. Okay. Good there. All right. So these are all physical things we can do to affect the rates. Okay. Keep in mind that generally the descriptions that I wrote down here all involve increasing the rate of reaction. But sometimes we don't want the reaction to go quickly. We want it to go slower. So whatever causes the reaction to go faster, if you do the opposite thing, it causes the reaction to go slower. Okay? It's the reason why, like, we want things to not spoil, right? Where do we put them? We want food not to go bad. Where do you put it? The refrigerator, right? Spoiling of food is a chemical reaction. That food changes into something else. If you make it colder, that reaction slows down. It doesn't happen as quickly. Stuff doesn't spoil as quickly. Okay? Good there? All right. Oh, sorry. Did I throw that on there? Yeah, I was ready to make a big, huge transition, and I forgot that was there. Oh. If we're talking about gases, a higher pressure is equivalent to a higher concentration. So same thing. All right, good there? Okay, next. There are some chemical factors that can affect the rate of this reaction. When we talk about chemical factors, now we're talking about the actual reactants that are in there. Changing something about the reactants that may increase or decrease the rate of that reaction. So first, we can talk about the size of a reactant molecule. Bigger molecules react more slowly than smaller molecules. That should be than. Bigger molecules react more slowly than smaller molecules. An example would be the gasoline that you put in your car. You guys don't have a car, but the gasoline that gets put into cars versus the liquid gasoline that you use in like a gas grill at home. Those molecules are different size, and the rates of reaction are a little bit different. It causes it to go faster or slower. Sometimes we want the rate to increase. Sometimes we don't want it to increase, depending on what we're looking at. And then the last thing we can do is add something called a catalyst. By definition, a catalyst is a substance that changes the reaction rate without being consumed or changed significantly. A catalyst is present with the reactants and the products of a reaction, but it does not necessarily participate in that reaction. Okay? An example, a practical example of a catalyst. Okay? This is like a real life example. Okay? So there are two people at school, and they don't like each other for whatever reason it might be. And tensions have been escalating all day long. Everybody knows that they're going to fight after school. Not that I condone that, it's just going to happen. Okay? So everybody gathers at the playground, because that's where fights happen, right, at the playground. So everybody gathers at the playground, and the two combatants come together, right? And then everybody surrounds them, right? Like a boxing ring, but of people, And they start verbally jawing with each other, right? Your mama is this, right? Whatever you want to go there, right? The catalyst, right, is the guy who stands there, and he's not part of the fight, but he's the guy who's like, oh, did you hear what he said about your mom? Are you going to let him say that? Are you kidding me? Right? And then the next guy says, he's like, oh, are you going to take that? You know? He's not going to be in the fight, but he's causing the fight to happen. Right? That's the catalyst. Right? It's not part of the reaction. It doesn't actually take part in the reaction, but it causes the rate of that reaction to go quicker. Right? Without that guy standing there, making sure that the other person heard what the other person said about their mom, right? That's ensuring that the fight's going to happen, or happen more quickly than it was going to on its own. Okay? It's not part of the reaction. It's just there to make things go a little quicker. Or sometimes we don't want it to go so quick, right? Sometimes we have something that's called an inhibitor. An inhibitor is a catalyst. It's just a catalyst in the other direction, right? If we go back to our scenario of the playground fight after school, what would the inhibitor be doing?
The guy who's trying to break up the fight.
Come on, guys, we don't have to do this, right? You're going to get in trouble, right? Trying to slow down that rate of the reaction, okay? It's still a catalyst, it just works the other way. This idea of catalyst is really, really important to your body and your physiology. Your body is full of substances that are called enzymes. Enzymes are biological catalysts. They're proteins, and you'll learn about proteins next year. But enzymes are catalysts that control reactions in living things. They speed up or slow down the rate at which your food is digested or your body reacts to different hormones or different substances or things like that, okay? They control the rates of reaction within your body because sometimes we need to speed them up, sometimes we need to slow them down, just depending on the situation, okay? But again, they don't take active part in those reactions. They just do something chemically to either inhibit or increase the rate of that reaction. Okay? Good there. All right. So that takes care of reaction rates. Again, going back to a little bit of what we talked about yesterday, right? The idea of how quickly do these things happen, how quickly is energy released, et cetera, et cetera, et cetera. Important when we're analyzing reactions as a whole.